So here we want to determine the convergence or divergence of the given series. And our series is the sum from n equals 1 to infinity of this expression. We have the square root of n² plus 8n minus 5, and then minus n, and that minus n is not underneath this square root. All right, and so if we want to determine if this series converges or diverges, the first thing that you should always try is the divergence test. And for the divergence test, we just take the limit as n approaches infinity of the sequence from our series and see if it doesn't equal 0. If that limit doesn't equal 0, then we know that the series will diverge. But if it does equal 0, then the results are inconclusive. It might still diverge, but it could also be a convergent series. And so let's start with the divergence test. Let's take the limit as n approaches infinity of this expression. So we'll have the square root of n² plus 8n minus 5 minus n. Okay? Now just by thinking about what happens to n as it approaches infinity for this expression, this n² is going to get bigger and bigger towards infinity. Then we're adding 8 times n, and that n is also approaching infinity. So we essentially have infinity plus another infinity. And so between these two terms, we just have a value that's getting bigger and bigger. And then we're subtracting 5, which is pretty much nothing compared to infinity. So really we have the square root of a very big number, a number that is increasing, or the square root of infinity, and then we are subtracting n, which is also approaching infinity. So this is a little bit of a weird limit. We could say that it's equal to infinity minus infinity, but that's not something that we actually know the value of. That would be an indeterminate form for this limit. You might be tempted to say that infinity minus infinity is 0, but we can't say that. That's not a thing that we can do. We don't really know the value of infinity, so subtracting it from itself doesn't really make sense. So we have to find a different way to go about evaluating this limit, because just looking at this expression as n approaches infinity is not going to be enough to evaluate it. And so what else can we do? Well, notice that in this expression here, we have a term with a square root, and then we're subtracting a term that doesn't have a square root. When you have an expression like this, something that can be helpful to do is multiply by a form of 1 of the conjugate of this expression. And what I mean by that is instead of having the square root of n² plus 8n minus 5 minus n, we're going to multiply by a form of 1 where we have the square root of n² plus 8n minus 5 plus n. All right, so here's what that will look like. We'll have the square root of n² plus 8n minus 5 plus n divided by itself. So we'll have the square root of n² plus 8n minus 5 plus n. And the reason why this is helpful is because now by multiplying this quantity by this quantity, we're going to have a very nice numerator. It's going to simplify nicely. Because essentially what we have here is the equivalent of a plus b times a minus b. And that is the factorization of a difference of squares, right? That would be equal to a² minus b². And comparing this to what we have here, a would be the same as the square root of n² plus 8n minus 5, and b would be the same as n. We have a minus b and a plus b. So multiplying these two quantities together is like having the factorization of a difference of squares. So we can rewrite it by just squaring this first term, which would be a, and subtracting the square of the second term. Now, if you didn't know that this could be seen as a difference of squares, you could just multiply these two quantities by each other and do the FOIL method, whatever you need to do, and you would find the same result. You would still get a² minus b², or this term squared minus this term squared. All right, so here's what we'll have. This will be equal to the limit as n approaches infinity of this term squared. So we're just going to remove that square root and have n² plus 8n minus 5. And then we're going to subtract this n². So we'll have minus n². That is the result of multiplying this quantity by this quantity. And then in the denominator, we're going to have this expression. So we'll have the square root of n² plus 8n minus 5 plus n. But now notice, in the numerator, we have a positive n² and a negative n², and so we can cancel those out. Those are just going to become 0, and so this is equal to the limit as n approaches infinity of 8n minus 5 divided by the square root of n²+8n minus 5 plus n. Okay, so now we have a much easier limit to work with here. Remember that we're still trying to figure out what this limit is equal to. For the divergence test, if this limit is not equal to 0, then we can conclude that this series diverges, but if it does equal 0, then we'll have to use some other test to show if it converges or diverges. But let's continue on. What happens to this expression as n approaches infinity? Well, in the numerator, we have 8n minus 5. If this n is approaching infinity, we have 8 times infinity, which is just infinity, and then subtracting 5, we're still going to have infinity. So in the numerator, we have infinity, and then we're dividing by this denominator, where we have the square root of n². As n approaches infinity and we're squaring it, it's just going to become bigger and bigger towards infinity. Then we're adding 8n. 8 times infinity is also getting bigger towards infinity. And then subtracting 5, not a big deal there. Subtracting 5 from infinity basically does nothing. So we have infinity under this square root, and the square root of infinity would just be infinity. If you take the square root of an increasing number, that square root is also increasing. And so we have an infinite value plus n, which is approaching infinity, so this denominator is just approaching infinity as well. It's just going to get bigger and bigger as n gets bigger. So the numerator and denominator are both getting bigger towards infinity, so this limit is in an indeterminate form of infinity divided by infinity, where we could use L'Hopital's rule. Now, I'm actually going to choose not to use L'Hopital's rule here. Remember that with L'Hopital's rule, if we have this indeterminate form, we could take the derivative of the numerator and denominator and then try evaluating the limit again, but this denominator is a little bit nasty. I'm not really looking forward to taking the derivative of this square root function, so I'm going to not do that. Instead, there's an easier method that we can do to quickly evaluate this limit as n approaches infinity. And this is a technique that goes back to early Calculus 1. What we can do to evaluate this limit as n approaches infinity is make use of a special limit. Remember that the limit as n approaches infinity of 1 divided by n will be equal to 0. And that's going to be true no matter what constant is in the numerator or the power of n in the denominator. We could have 7 divided by n, and the limit as n approaches infinity is still 0. We could have 7 divided by n², and the limit as n approaches infinity will still be 0. As long as we have this general form of a constant divided by n raised to some positive power, then this special limit holds true. We can use that to our advantage in this limit by multiplying by a form of 1 of an expression similar to this limit. Now I'm just going to rewrite this to be 1 divided by n again. That's the most basic case. But what form of 1 should we multiply by this limit? Well, what you do is you look for the highest power of n in the numerator or denominator and multiply by a form of 1 divided by n raised to that power. In this case, the highest power of n that I see is 1. Even though we have this n² here, it's underneath a square root, and so that square root and that n² kind of cancel each other out in a way. Right, remember that the square root of a value is the same as that value to the 1/2 power. So if that value is squared, let's say we have x², then you would have x² to the power of 1/2. And so if you were to simplify this expression, x² to the 1/2 power, you'd multiply the exponents. 2 times 1/2 is 1. So really, the degree of the denominator, or the highest power of n, is 1. And that's the same as the numerator. So here's what we can do. We can multiply by a form of 1 divided by n to the first power, except in the denominator, I'm going to rewrite it slightly different. We'll write it like this. We'll have the square root of 1 divided by n², right? That would be the same thing as 1 divided by n. The square root of 1 is 1, and the square root of n² is n. We write it this way so that we can multiply 1 divided by n² into this square root function. By having it underneath a square root, we can multiply that value through those terms. Now for this n on the outside, we're just going to be multiplying by 1 divided by n, which would be the square root of 1 divided by n². All right, but we'll get to that. Let's simplify what we have here. This will be equal to the limit as n approaches infinity of 8n times 1 divided by n. That's just going to leave us with 8. That n will cancel out with that n. And then we'll have minus 5 divided by n. We multiplied -5 by 1 divided by n. Now in the denominator, we'll have this square root, but then n squared times 1 divided by n squared is 1. So we have the square root of 1 plus 8n times 1 divided by n squared. That will leave us with 8 divided by n. And then we have -5 times 1 divided by n squared, which will give us -5 divided by n squared. And then outside the square root, we have this plus n. We're multiplying that by 1 divided by n. That's what this would also be equal to, like I said. So we have n times 1 divided by n, which just results in 1. Okay? Now the reason why that's helpful is because now we can take the limit as n approaches infinity through the numerator and denominator, remembering this special limit, and we'll be able to evaluate this limit. All right, so here's what we're going to have. The limit as n approaches infinity of a constant will just be that constant. So we have 8 minus the limit as n approaches infinity of 5 divided by n, which is 0, right? Some constant divided by n. The limit as that n approaches infinity will be 0, and then we're dividing by the limit as n approaches infinity of the square root of 1, which will still be 1, and then we have plus 8 divided by n. The limit of that will be 0, and then minus 5 divided by n squared. The limit of that will also be 0, or at least the limit as n approaches infinity. So we have 1 plus 0 minus 0, and then that plus 1 on the outside. The limit as n approaches infinity of plus 1, or positive 1, is just going to be 1. All right, and remember that that is equal to that limit. All right, now to simplify, 8 minus 0 is 8. So this is equal to 8 divided by the square root of 1 plus 0 minus 0. So we have the square root of 1 plus 1. The square root of 1 is 1, so we have 1 plus 1, which is 2. So this is equal to 8 divided by 2, which is equal to 4. And 4 is not equal to 0, right? 4 is bigger than 0. And so if 4 is a result of this limit as n approaches infinity for the sequence from our series, then we can conclude from the divergence test that this series is a divergent series. So we can conclude that our series diverges. That is the final answer to this problem. Okay, and so with that, that's it for this example. But if you do want to see some more examples of using the divergence test for series, feel free to check out the video that I have linked here on the screen. And if you want to learn more about some other topics in Calculus 2, feel free to check out the playlist that I have linked here on the screen, where you can find all of my Calculus 2 videos. Okay, if you have any questions, feel free to leave those in the comments, but if you don't have any questions, this is all I had for now, so I will see you next time.